Light and photoreceptor arrangement. The reason why this is an important concept is because it seems a bit counterintuitive. Light is traveling down towards the pigment epithelium. It's interesting it travels through these cells to get to the photoreceptor layer and the pigment epithelium. The pigment epithelium is going to have chromophores in it, very similar to melanin, which is in your skin, to absorb light. Chromophores, again, are particles that absorb light. Photoreceptors are located just superficial to the pigment epithelium, and these will be what are going to respond to those photons of light. Some of these here are rods and some of them are cones, but both of them will respond to various forms of light. But interesting, the light is traveling through all these layers of nerves to get to this particular point. Looking at photoreceptors in more detail, you can see the rod structure and the cone structure. There's a couple different segments that we need to highlight here. You have the synaptic terminals, where are the points at which the photoreceptor will interface with a bipolar cell. You have the inner segments. The inner segments have the stuff of the cell, the cytoplasm, it has some of the mitochondria, it has the nucleus, and then you have the outer segments, and this is what has these specialized photoreceptor response elements. In the rod, they look like little discs. In the cone, they look like evaginations. And so you can see how they named rods and cones based upon how they look in terms of the histology, how they work. So the photoreceptor part in the rod is going to be those discs. Those discs have a molecule called rhodopsin in them. Rhodopsin is a protein hooked to a retinol molecule. So the opsin is the protein and the rho is the retinol component. It starts out in this 11 cis retinol configuration bound to the opsin molecule. If light is present, this 11 cis retinol molecule conformationally changes to an all-trans retinol. When this all-trans conversion happens, it causes a further conversion to the rhodopsin molecule and forms this metarhodopsin 2. This activates a G protein coupled receptor, and this G protein is transducin. Transducin activates an enzyme called phosphodiesterase, and if you remember what a phosphodiesterase does, it changes either cyclic AMP or cyclic GMP back to its original form, in this case 5' GMP. Why this becomes important is it decreases cyclic GMP within the cell. Cyclic GMP has an important function in that it is linked to sodium channels. If you have high levels of cyclic GMP around, you'll have these sodium channels open to a greater degree. If you decrease cyclic GMP, you close these sodium channels. The closure of the sodium channels hyperpolarize the photoreceptor membrane. Why this is important? The hyperpolarization allows for a greater amount of on versus off component of the photoreceptor. So if light is present, you get hyperpolarization. If light is absent, you get depolarization. That's a little bit different than some receptors that we have talked about thus far in physiology. So remember, light hyperpolarizes, dark depolarizes.